Tonight, we're going to explore one of the oldest and most surprisingly difficult questions ever asked about the cosmos. Where is the center of the universe? At first, the question feels almost unavoidable. Every city has a center, every circle has a center, even the planets revolve around stars with recognizable points of balance. It seems only natural to wonder whether the entire universe must also possess one hidden location from which everything began or around which everything is somehow arranged. For thousands of years, people have searched the heavens, believing they occupied a special place within creation. As astronomy matured, that certainty slowly faded. Earth was no longer the center of the solar system. The Sun proved to be an ordinary star within an ordinary galaxy. Even our Milky Way lost its privileged position among countless billions of galaxies stretching across unimaginable distances. Yet the question remained, if nothing else is central, could the universe itself still have a single, unique middle? Over the next hour, we will follow the trail left by astronomers, mathematicians, physicists, and generations of increasingly powerful telescopes. We will examine the observations that reshaped our understanding of space, the discoveries that challenged intuition, and the evidence that continues to guide modern cosmology. Along the way, we will separate what has been measured from what has merely been proposed, and what remains one of science's most enduring mysteries. If you enjoy thoughtful journeys through the cosmos, consider leaving a comment about where you're listening from, and subscribe for more quiet explorations of the universe. Our investigation begins not with distant galaxies or exotic theories, but with a simple assumption so familiar that most of us rarely stop to question it. We naturally expect every vast structure to possess a center. But what if the universe refuses to follow the rules that govern everything we experience in everyday life? The question of a cosmic center feels so intuitive because it grows directly from the world we know. Every landscape has a highest point. Every wheel has a hub. Every sphere has a middle hidden beneath its surface. From childhood, we learn to understand objects by locating their boundaries and identifying the point around which everything else is arranged. The larger the object becomes, the more natural it seems to ask where its center lies. For most of human history, that instinct appeared to match the heavens themselves. When ancient civilizations looked upward, the sky seemed to rotate around a motionless earth. The sun rose each morning in the east, crossed the sky with remarkable regularity, and disappeared beyond the western horizon. The moon followed its changing cycle, while the stars swept across the night in graceful arcs. To careful observers, the simplest explanation was that everything revolved around us. This picture became remarkably sophisticated. Ancient Greek astronomers, particularly Aristotle and later Claudius Ptolemy, developed detailed models in which Earth occupied the exact center of the cosmos. Around it moved the moon, the sun, the known planets, and finally the distant sphere of fixed stars, although these models would eventually prove incorrect. They were built upon genuine observation and represented humanity's earliest serious attempt to explain the structure of the universe. For many centuries, the geocentric universe felt complete. It was not merely a philosophical preference, it was a practical framework that predicted celestial motions with surprising accuracy for its time. The sky behaved as though Earth were standing still, while everything else moved around it. Yet nature often rewards deeper observation with unexpected complexity. As telescopes improved during the 17th century, astronomers began noticing details invisible to earlier generations. The phases of Venus resembled those of our moon, something difficult to explain if Venus orbited Earth. Jupiter possessed 4 large moons of its own, demonstrating that not everything revolved around our planet. The rough mountains of the moon and the dark spots drifting across the sun challenged the long-held belief that the heavens were perfectly unchanging. Gradually, the center began to move. The work of Nicolaus Copernicus placed the sun at the heart of the solar system. Johannes Kepler showed that planets travel along ellipses rather than perfect circles. Isaac Newton later explained that gravity governed these motions through a universal law applying equally on Earth and in the heavens. The shift was profound. Humanity had not simply rearranged the planets, it had surrendered its privileged position. But the sun's apparent importance did not survive forever either. During the 18th and 19th centuries, astronomers slowly realized that the stars surrounding the Sun formed an immense stellar system now known as the Milky Way. At first, many believed our Sun occupied its center. Once again, familiarity encouraged symmetry. Surely the star we lived beside must occupy the middle of this magnificent galaxy. Observations gradually suggested otherwise. By studying the distribution of star clusters and the effects of interstellar dust, astronomers eventually discovered that the Milky Way's true center lies roughly 26,000 light-years away, in the direction of the constellation Sagittarius. There, hidden behind dense clouds of gas and dust, resides a supermassive black hole known as Sagittarius A star, containing about 4 million times the mass of our Sun. The realization was quietly humbling. The solar system circles the galactic center once every approximately 230 million years. During the lifetime of the dinosaurs, our planet occupied an entirely different region of the Milky Way. Every person who has ever lived has done so while traveling through the galaxy at roughly 220 kilometers per second, carried along by an orbit too vast to perceive directly. Even our galaxy proved not to be unique. By the early 20th century, observations revealed that the faint spiral nebulae scattered across the sky were not nearby clouds within the Milky Way. They were galaxies in their own right, each containing hundreds of billions of stars. The universe expanded almost overnight. Instead of one galaxy surrounded by empty space, astronomers now faced a cosmos populated by countless island universes, stretching far beyond anything previously imagined. With each new discovery, another center disappeared. Earth was not the center of the solar system. The Sun was not the center of the Milky Way. The Milky Way was not the center of the observable cosmos. A pattern was beginning to emerge. Every time humanity identified what seemed to be a privileged location, better observations revealed it to be ordinary instead. This gradual displacement became one of the guiding ideas of modern astronomy. Often called the Copernican principle, it suggests that our location in the universe is not fundamentally special. While not a physical law, it has repeatedly proven to be an extraordinarily successful assumption, time after time. Nature has resisted the temptation to place humanity at the center of the grandest structures we discover. Yet one final question remained untouched. Perhaps no planet, no star, and no galaxy occupies the center. But could the universe itself still possess one? Unlike a galaxy whose stars clearly orbit a common gravitational focus, the universe contains every galaxy. There is nothing obviously outside it from which to view its complete shape. We cannot step back and photograph the cosmos from afar. Every observation we make begins from a single location embedded deep within it. That simple limitation changes everything. When astronomers point their telescopes into space, they are always looking outward from Earth. Every measurement of distance, every map of galaxies, every image captured by the largest observatories forms a view centered on our own position. This does not mean Earth occupies a privileged place. It simply reflects the unavoidable fact that every observer sees the universe from wherever they happen to be. This subtle distinction is easy to overlook. If every observation naturally spreads outward from the observer, how can anyone determine whether there exists another point that is truly central? The answer seems straightforward at first. Measure the distances to enough galaxies, chart their positions, and identify the middle. Yet when astronomers finally began making those measurements with increasing precision, the universe responded with something deeply unexpected. Instead of revealing a hidden center, the galaxies themselves appeared to be telling an entirely different story. Section 30. At the beginning of the 20th century, astronomers believed they were on the verge of solving the largest map ever attempted. Telescopes had grown more powerful than any built before. Photography allowed faint objects to be recorded over many hours rather than glimpsed for only a moment through an eyepiece. Spectroscopy had revealed that starlight carried information about temperature, composition, and motion. Piece by piece, the universe seemed ready to surrender its geometry. The first task appeared simple: measure how far away the galaxies are. Once their distances are known, plot them in 3 dimensions. If the universe has a center, perhaps the pattern will reveal it naturally. Yet even this first step proved extraordinarily difficult. Distance is one of astronomy's greatest challenges because space offers no measuring tape. A nearby mountain can be reached with a journey, a distant city can be surveyed from multiple locations, a galaxy millions of light years away cannot. Astronomers instead build what is often called the cosmic distance ladder. Each rung depends upon one below it. The nearest stars reveal their distances through parallax, the tiny shift in position caused by Earth's orbit around the Sun. Once those distances are known, astronomers can calibrate the true brightness of certain types of stars. Those stars then become standard candles, allowing much greater distances to be estimated. Still brighter objects extend the ladder even farther until entire galaxies become measurable. Every step introduces uncertainty. Small errors near the bottom can grow larger as measurements extend across millions or billions of light years. Throughout much of the early 20th century, astronomers debated the true scale of the universe because different methods often produced different answers. Even so, an astonishing picture slowly emerged. Galaxies were not scattered randomly around the Milky Way. They stretched outward in every direction. Some were relatively close, only a few million light years away. Others occupied distances so immense that their light had begun its journey before the first animals walked upon land. As telescopes improved, every apparent edge dissolved into still more galaxies beyond. If a center existed, perhaps it could be identified statistically. One might expect galaxies to become denser in one direction and thinner in another, much as trees become more concentrated when approaching the middle of a forest. Instead, the sky appeared remarkably balanced. No matter where astronomers looked, galaxies seemed to populate the heavens in roughly similar numbers. Once observational limitations were taken into account, this apparent uniformity became known as isotropy. The word simply means that the universe looks broadly the same in every direction. It does not imply that every region is identical. Individual galaxies, clusters, and enormous voids certainly exist, but averaged over sufficiently large distances, the cosmos displays a surprising degree of symmetry. At first glance, isotropy might seem to support the idea that Earth occupies the center. After all, if everything looks evenly distributed around us, does that not suggest we stand in the middle? The answer depends entirely upon perspective. Consider standing within a vast fog. The mist surrounds you equally in every direction. Visibility fades at roughly the same distance no matter where you turn. Yet nothing about that experience tells you whether you are standing at the center of the fog or simply somewhere inside it. Another observer several kilometers away would describe the same scene. Neither person's experience reveals the true shape of the cloud. Astronomy faces a similar limitation. Every observation begins from one location inside the universe. Symmetry around the observer does not automatically imply centrality. This subtle distinction became even more intriguing once astronomers began studying the light emitted by galaxies themselves. When light passes through a prism, it separates into its component colors, producing a spectrum crossed by distinctive dark or bright lines. These spectral lines act like fingerprints, allowing scientists to identify chemical elements with remarkable precision. More importantly, they also reveal motion. If an object moves toward an observer, its spectral lines shift slightly toward shorter wavelengths, producing what is called a blue shift. If it moves away, the lines shift toward longer wavelengths, creating a redshift. The effect is familiar in everyday life through sound. The pitch of a passing ambulance siren changes as it approaches and then recedes. Light behaves similarly, although the change occurs in wavelength rather than sound frequency. During the early decades of the 20th century, astronomers began measuring the spectra of distant galaxies in increasing numbers. They expected to find a mixture. Some galaxies should be approaching, others should be moving away. Perhaps large-scale motions around a cosmic center would eventually emerge. Instead, something profoundly unexpected appeared. Nearly every distant galaxy exhibited a redshift. Almost all seemed to be moving away from us. The farther the galaxy, the greater its redshift tended to become. A result was met with caution. Perhaps the measurements were incomplete. Perhaps local motions produced an illusion. Perhaps our own galaxy occupied a special position after all. For a brief moment, the observations almost invited humanity back toward the center it had gradually abandoned. If every galaxy appears to be rushing away from Earth, could that mean we truly occupy the middle of the universe? The possibility was tempting because it agreed with everyday intuition. When an explosion occurs, fragments race outward from a central point. Stand at that point, and everything moves away. Stand elsewhere, and the pattern becomes uneven. Many people naturally imagine the universe behaving the same way, yet the comparison concealed a crucial assumption. An explosion expands into pre-existing space. The universe might not. That distinction had not yet become clear. The observations alone could not determine whether galaxies were flying through space from a single origin, or whether something more subtle was taking place. Astronomers possessed measurements. They possessed spectra. They possessed growing catalogues of galaxies, but they still lacked the conceptual framework capable of explaining what those measurements truly meant. Nature had provided the evidence before humanity possessed the language to interpret it. The redshifts were real. The distances were becoming increasingly reliable. The apparent recession of galaxies could not simply be dismissed. But if every observer sees distant galaxies moving away, how can anyone identify a unique center? The answer would emerge not from another telescope alone, but from the remarkable convergence of observation, mathematics, and one of the most transformative discoveries in the history of astronomy. Soon. A careful analysis of galaxy distances and their motions would reveal a relationship so simple that it could be written as a straight line on a graph, yet so profound that it would forever change how humanity understood the universe itself. The story of one of astronomy's greatest discoveries begins long before the famous graph that would eventually bear Edwin Hubble's name. Like many turning points in science, it was not the work of a single individual, but the gradual convergence of new technology, patient observation, and ideas whose significance only became clear when viewed together. By the opening years of the 20th century, astronomers had reached an uncomfortable boundary. Their telescopes revealed countless faint spiral nebulae scattered across the night sky, but no one could say with confidence what these objects truly were. Two possibilities competed. One proposed that the spirals were relatively small clouds of gas lying within the Milky Way. If this were true, our galaxy constituted almost the entire universe. The other suggested something far more astonishing. Perhaps each spiral nebula was itself a vast collection of stars, comparable to the Milky Way but unimaginably distant. If so, the universe would be vastly larger than anyone had previously imagined. The disagreement became so significant that in 1920 it was formalized in what later became known as the Great Debate. The astronomers Harlow Shapley and Heber Curtis presented opposing interpretations before the National Academy of Sciences in Washington, D.C. Shapley argued for an enormous Milky Way containing the spiral nebulae within it. Curtis maintained that many spirals were independent galaxies existing far beyond our own. Both scientists relied upon genuine evidence. Both also lacked the decisive observation needed to settle the question. The answer would arrive from a mountain overlooking Southern California. High above the haze of Los Angeles stood the newly completed Hooker telescope at Mount Wilson Observatory. With a mirror 100 inches across, it was the most powerful optical telescope in the world. Its enormous light-gathering ability allowed astronomers to detect objects far fainter than ever before. Among those using the telescope was a young astronomer named Edwin Hubble. Hubble possessed patience as much as brilliance. Rather than searching for dramatic discoveries, he carefully examined photographic plates of the spiral nebulae, comparing images taken weeks apart. One particular object captured his attention. Today we know it as the Andromeda Galaxy. At the time, many still referred to it simply as the Andromeda Nebula. Within its faint spiral arms, Hubble identified tiny stars whose brightness changed in a regular cycle. These were Cepheid variable stars. Only a few years earlier, the astronomer Henrietta Swan Leavitt had made a remarkable discovery while studying thousands of variable stars in the Magellanic Clouds. She found that the longer a Cepheid takes to brighten and dim, the greater its true luminosity. The relationship transformed astronomy. If the intrinsic brightness of a Cepheid is known, comparing it with its apparent brightness reveals its distance. It was as though nature had provided astronomers with a collection of standard candles scattered throughout the cosmos. Leavitt's discovery supplied the ruler. Hubble used that ruler. When he calculated the distance to the Cepheid variables in Andromeda, the result was unmistakable. The stars were far too distant to belong to the Milky Way. Andromeda was an entirely separate galaxy. Its light had travelled roughly 1 million light-years according to the measurements available at the time. although modern observations place the distance at about 2.5 million light-years. The exact number changed as techniques improved, but the conclusion did not. The universe had suddenly become immeasurably larger. The Milky Way was no longer the whole cosmos. It was one galaxy among many. Almost overnight, the known universe expanded from a single stellar system into a vast population of galaxies stretching across unimaginable distances. Yet Hubble's most famous contribution was still to come. Distances alone could not reveal how the universe behaved. Astronomers also needed to know whether galaxies were moving. Fortunately, another astronomer had already spent years collecting precisely the information required. At the Lowell Observatory in Arizona, Vesto Melvin Slipher had been measuring the spectra of spiral nebulae since 1912. Using painstakingly long photographic exposures, sometimes lasting many nights, Slipher determined the Doppler shifts of these distant objects. His results were extraordinary. Most spiral nebulae exhibited strong redshifts. They appeared to be receding from Earth. For years, the significance of Slipher's measurements remained uncertain because no one knew how far away the nebulae actually were. Redshifts, without distances, could reveal motion but not the larger pattern. Hubble now possessed the missing ingredient. By combining his distance measurements with Slipher's redshift data, a remarkable relationship emerged. Galaxies that were farther away generally exhibited larger redshifts. The relationship was approximately linear. Double the distance, and the recession speed roughly doubled. Triple the distance, and the recession appeared greater still. The pattern became known as Hubble's law. Although historians of science increasingly acknowledge the essential contributions of Slipher, and later the Belgian priest and physicist Georges Lemaitre, who independently derived the relationship and connected it to solutions of Einstein's equations before Hubble's famous publication, the graph itself appeared almost deceptively simple, a straight line. Yet behind that line lay one of the deepest revelations in the history of science. The universe was not static. On the larger scales, galaxies were moving farther apart. This conclusion challenged one of the strongest assumptions of the age. Even Albert Einstein had originally introduced what he called the cosmological constant into his equations of general relativity, because he believed the universe must be eternal and unchanging. Without that additional term, his equations naturally predicted either expansion or contraction. Nature, however, seemed to favor expansion. Lemaitre recognized this possibility remarkably early. Drawing upon Einstein's theory and the growing observational evidence, he proposed that the universe itself could be expanding from an earlier, denser state. It was a bold interpretation. At first, many scientists found it difficult to accept. Expansion sounded strangely like motion through empty space. It encouraged a familiar picture: galaxies rushing outward from a central explosion, a cosmic firework whose fragments continued to fly apart. If this image were correct, then tracing every galaxy backward should reveal a single point in space from which they all emerged. That point would naturally seem to be the center of the universe. The idea felt convincing because it echoed experiences from everyday life. Throw a stone into a pond. The ripples spread outward from one location. Watch fireworks. Fragments race away from the place where the shell exploded. Observe shrapnel after an explosion. Every piece carries information about the original center. It was tempting to assume that cosmic expansion worked in exactly the same way, but astronomers soon realized that the observations contained a subtle contradiction. No matter which galaxy one considered, the overall pattern of expansion appeared remarkably similar. If intelligent observers lived within Andromeda, they would also see distant galaxies moving away. An observer inside the Whirlpool galaxy would describe much the same behavior. The recession pattern did not appear unique to Earth. This was profoundly different from an ordinary explosion. An explosion has one privileged origin. The expanding universe seemed to have none. The measurements were becoming increasingly precise. Yet the intuitive picture grew increasingly inadequate. Hubble's observations had demonstrated that galaxies separate with distance. They had not shown that they were flying away from a single location embedded within space. To understand what the data truly implied, astronomers would need to reconsider an assumption so fundamental that it often passed unnoticed. Perhaps it was not the galaxies moving through space that mattered most. Perhaps it was space itself. That possibility would transform the search for the center of the universe from a question about location into a question about the very nature of reality. The discovery that distant galaxies appear to recede from one another invited a picture that seemed almost irresistible. Most people, including many scientists during the early years of modern cosmology, naturally imagined the universe as an enormous explosion. Matter must have been concentrated at one point, they reasoned, before being hurled outward into an already existing emptiness. If that were true, then somewhere, however distant, there should still be a location marking the beginning of the expansion. Yet as astronomers continued observing the cosmos, this familiar image became increasingly difficult to reconcile with the evidence. The difficulty did not arise because the galaxies behaved unexpectedly. Their motions, measured through redshift, continued to support the conclusion that the universe is expanding. The problem lay in the geometry of the expansion itself. Suppose every galaxy was simply traveling through space after a colossal explosion. Galaxies closer to the original center would eventually occupy different regions than those farther away. Their motions would preserve subtle clues about where everything began. Somewhere in the sky, astronomers should eventually detect a preferred direction. One side of the universe would appear fundamentally different from the other. Instead, observations continued to reveal remarkable uniformity. The deeper telescopes looked, the more the large-scale universe appeared statistically similar in every direction. This realization encouraged astronomers to think less about individual galaxies and more about the fabric in which those galaxies exist. General relativity had already transformed gravity from a force acting across empty space into something more subtle. According to Einstein's theory, matter and energy influence the geometry of space-time itself. Massive objects curve that geometry, and other objects follow those curves. Planets orbit stars not because they are pulled along invisible strings, but because they travel through curved spacetime. If spacetime could bend, perhaps it could also change its scale. Perhaps expansion was not galaxies racing across an unchanging stage. Perhaps the stage itself was slowly growing larger. This idea can feel abstract because nothing in everyday life behaves quite the same way. Consider an old woven fabric laid flat upon a table. The threads, crossing one another, define the structure of the cloth. Tiny beads sewn onto that fabric remain attached to their individual threads. Now imagine the entire cloth stretching evenly in every direction. The beads separate from one another. None of them need slide across the fabric. Instead, the fabric between them grows. Each bead sees every sufficiently distant bead moving away. No bead occupies a privileged location. No bead can identify itself as the center merely by observing the increasing distances. The analogy is imperfect, as all analogies are. The cloth expands into the surrounding room. Whereas modern cosmology does not require the universe to expand into any external space at all, nevertheless it captures one crucial distinction. Expansion need not mean motion through space. It can instead mean the changing geometry of space itself. This subtle shift in perspective resolved several puzzling observations at once. If every region of space expands similarly on sufficiently large scales, then every observer naturally sees distant galaxies receding. The pattern does not require Earth to occupy a special position. An astronomer living billions of light years away would draw much the same conclusion. The universe would appear centered on every observer without possessing a unique central location. At first glance, this sounds contradictory. How can every observer appear central if only one true center can exist? The answer depends upon abandoning assumptions inherited from ordinary objects. A galaxy has an edge. A football has a surface. A sphere has a center because its boundaries define one. The universe may not possess comparable boundaries. Modern cosmology distinguishes carefully between the observable universe and the universe as a whole. The observable universe consists of everything whose light has had sufficient time to reach us since the beginning of cosmic expansion. Because light travels at a finite speed, we cannot observe beyond a certain distance. That limit is not a physical wall. It is simply the greatest distance from which information has had time to arrive. Today, that observable region extends roughly 46 billion light-years in every direction, even though the universe itself is about 13.8 billion years old. The greater distance arises because space has continued expanding while the light traveled toward us. Every observer possesses such an observable sphere. An astronomer in another galaxy would also occupy the center of their own observable universe. Their cosmic horizon would surround them just as ours surrounds us. These horizons overlap enormously, yet none identifies the center of the entire cosmos. The distinction is easy to confuse because every astronomical image is inevitably centered on the observer. When we examine maps of the cosmic microwave background, galaxy catalogues, or deep field surveys, Earth appears near the middle. Not because Earth is cosmically privileged, because every map begins where the measurements begin. It resembles drawing a map of visible mountains while standing in a valley. Naturally, your own location appears at the center of your observations. Another traveller elsewhere would produce a different map centered upon themselves. Neither map reveals the full geography. As galaxy surveys expanded during the late 20th century, astronomers uncovered another remarkable feature. Galaxies are not sprinkled evenly like grains of sand. Instead, they form an immense cosmic web. Clusters of galaxies gather at the intersections of enormous filaments stretching hundreds of millions of light-years across. Between these filaments lie gigantic voids containing relatively few galaxies. The scale is astonishing. Some voids exceed 300 million light-years in diameter. The filaments connecting clusters create patterns resembling neural networks, branching rivers, or the delicate foam left behind by retreating waves. Despite their beauty, these structures do not point toward a universal center. On sufficiently large scales, the cosmic web itself becomes statistically uniform. Individual features vary enormously, but averaged over hundreds of millions of light-years, no preferred direction or privileged location emerges. This principle, known as cosmic homogeneity, complements isotropy. Isotropy tells us that the universe looks similar in every direction. Homogeneity suggests that sufficiently large regions resemble one another, regardless of where they are located. Together, these ideas form the cosmological principle, one of the central assumptions underlying modern cosmology. Importantly, it remains an assumption because no one can observe the entire universe directly. Scientists adopt it because every increasingly precise observation has continued to support it within the observable cosmos. The principle has survived decades of increasingly detailed galaxy surveys, studies of the cosmic microwave background, and measurements of large-scale structure. Yet assumptions, however successful, are never beyond examination. Astronomers continue testing the cosmological principle because even a small violation could reshape our understanding of the universe. What if one region were expanding differently? What if an enormous hidden structure distorted our observations? What if the apparent uniformity concealed something deeper? These possibilities remain subjects of active investigation. For now, however, the evidence points consistently in one direction. The universe behaves very differently from an ordinary explosion. Space itself expands. Every distant observer witnesses similar expansion. No obvious edge has been discovered. No preferred direction has emerged, and no observational evidence has identified a unique cosmic center. Yet this conclusion raises an even deeper question. If the universe has no observable center, why do the mathematical models describing it work so remarkably well? What hidden assumptions allow these equations to describe billions of galaxies with extraordinary accuracy, while still leaving one profound mystery unresolved? For centuries, the search for the center of the universe seemed like a geographical problem. Find the correct direction. Travel far enough. Eventually, the middle should appear. Modern cosmology has transformed that simple question into something far more subtle. Today, the mystery is no longer where the center might be. Instead, scientists ask whether the question itself is physically meaningful. This is the first great mystery. It begins with one of the most successful ideas in all of astronomy, the cosmological principle. Although its name sounds imposing, the principle expresses a remarkably modest assumption. On sufficiently large scales, the universe is both homogeneous and isotropic. In other words, no location appears fundamentally different from another, and no direction appears fundamentally special. It is important to recognize what this does and does not mean. The universe is clearly not uniform on small scales. Stars gather into galaxies. Galaxies gather into clusters. Clusters connect through immense filaments. Gigantic voids separate these structures. If someone were standing inside one of those voids, their immediate surroundings would differ dramatically from someone living inside the Virgo cluster. The cosmological principle ignores those local differences. Instead, it asks what happens when we zoom out far enough. A useful comparison comes from standing on a beach. At your feet, every grain of sand occupies a unique position. Tiny shells, scattered pebbles, and footprints create endless irregularity. Walk several kilometers above the shoreline in an aircraft, and those details disappear. The coastline begins to reveal broad patterns invisible from the ground. Cosmology performs a similar act of averaging. When astronomers examine hundreds of millions of light years instead of individual galaxies, the irregularities begin to smooth together. This statistical simplicity has extraordinary consequences. Albert Einstein's general theory of relativity describes how matter, energy, space, and time interact. The equations themselves are notoriously difficult. They allow countless possible universes, each evolving according to its own geometry, without simplifying assumptions. Solving those equations for an entire universe filled with billions upon billions of galaxies becomes essentially impossible. The cosmological principle provides the simplification. If the universe possesses no preferred location and no preferred direction on sufficiently large scales, the equations become dramatically more manageable. During the early 1920s, the Russian mathematician Alexander Friedmann discovered that Einstein's equations naturally permitted expanding universes. Soon afterward, Georges Lemaitre independently reached similar conclusions while connecting them to astronomical observations. Neither scientist invented expansion. Rather, they found that Einstein's own theory almost demanded it once the assumption of large-scale uniformity was introduced. From these solutions emerged what cosmologists now call the Friedmann-Lemaitre-Robertson-Walker models, often shortened simply to FLRW models. Despite the intimidating name, their central idea is surprisingly elegant. The universe changes with time. Its overall geometry expands or contracts. Yet every sufficiently large region evolves according to the same underlying rules. The mathematics contains no distinguished center, not because scientists deliberately removed one, because the assumptions supported by observation never require one. This distinction matters enormously. Suppose astronomers suddenly discovered overwhelming evidence that one region of the universe behaved differently from every other region. Perhaps galaxies systematically became younger in one direction. Perhaps the average density increased steadily toward a particular location. Perhaps cosmic expansion accelerated differently across opposite sides of the sky. Any of these findings would challenge the cosmological principle. The equations themselves would need revision. The possibility of a genuine center would immediately become worthy of serious investigation. Science, therefore, does not reject a cosmic center out of preference. It rejects it because observations have consistently failed to reveal the asymmetries such a center would likely produce. Even so, an uncomfortable question remains. If the universe has no center today, what about the beginning? Modern cosmology traces the observable universe backward toward an early state that was extraordinarily hot and extraordinarily dense. This description is often summarized by the phrase, the Big Bang. Unfortunately, those two words have inspired one of the most persistent misunderstandings in science. The name itself encourages the image of an explosion. Explosions occur at specific places. They expand outward into surrounding space. They possess identifiable centers. The Big Bang, according to accepted cosmology, was fundamentally different. It was not matter exploding into empty space. It was the earliest known state of the expanding universe itself. Every region of today's observable cosmos was once vastly closer together than it is now. Space did not burst outward from one location. Rather, space everywhere evolved from a much denser condition. The distinction is subtle enough that even professional physicists often rely on careful language to avoid misunderstanding. Asking where the Big Bang happened resembles asking where the surface of Earth begins. The question quietly assumes a framework that may not exist. There is another misconception equally common. Many people picture the early universe as a tiny ball floating inside an infinite emptiness. The ball expands. Eventually, it becomes the cosmos we observe today. Yet nothing in standard cosmology requires such an external emptiness. The mathematical models describe space itself. They do not require another space surrounding it. Whether anything exists beyond the universe, or whether the concept of beyond is meaningful at all, remains an open philosophical and scientific question. Current observations cannot answer it. The mystery grows deeper still when we consider time. As we look farther into space, we also look farther into the past because light requires time to travel. A galaxy 1 billion light-years away appears as it existed 1 billion years ago. The most distant observable light, the cosmic microwave background, comes from a time roughly 380,000 years after the beginning of cosmic expansion. Beyond that point, the universe was so hot that light could not travel freely. Our observational window closes. The earliest moments remain hidden behind a veil that current telescopes cannot penetrate directly. This limitation means cosmologists reconstruct the first fractions of a second using theory supported by indirect evidence rather than direct observation. The distinction is essential. The expansion of the universe is an observed fact. The cosmic microwave background is an observed fact. The abundances of light elements are observed facts. The detailed physics governing the very first instant remains an area of active theoretical research. Several competing ideas attempt to describe it. None has yet achieved complete observational confirmation. This is where scientific certainty begins to soften. The farther backward cosmologists travel, the fewer direct observations remain available. Eventually, known physics itself approaches its limits. General relativity successfully describes gravity across enormous cosmic distances. Quantum mechanics successfully describes the microscopic world near the earliest moments of cosmic history. Both theories become simultaneously important, yet they do not currently merge into one complete description. A successful theory of quantum gravity remains one of the greatest unsolved problems in modern physics. Without it, questions about the exact beginning of spacetime remain incomplete. That uncertainty has profound consequences for the search for a center. If our understanding of the earliest universe is unfinished, could our picture of cosmic geometry also be incomplete? Might future observations reveal subtle departures from perfect uniformity? Could hidden features exist beyond the observable horizon? Or have decades of increasingly precise measurements already pointed us toward a universe where the idea of a central location is simply the wrong question to ask? To approach those possibilities, astronomers must rely on something more dependable than intuition. They must follow the evidence itself, allowing the oldest light in the universe and the largest maps ever created to speak before theory does. The search for the center of the universe ultimately depends upon a simple principle that guides all of science. If a claim concerns the physical universe, it must eventually confront observation. No matter how elegant an idea may seem, no matter how satisfying it feels to human intuition, astronomers must ask a more demanding question. What can actually be measured? This distinction has shaped modern cosmology from the beginning. Many of our deepest questions reach beyond direct experience. We cannot travel to another galaxy within a human lifetime. We cannot step outside the universe to photograph it from afar. We cannot witness the earliest instant of cosmic history with our own eyes. Yet remarkably, the universe leaves behind evidence. Light carries information across billions of years. Gravity subtly bends the paths of distant galaxies. The distribution of matter records the history of cosmic evolution. Like ancient fossils embedded within rock, these clues preserve traces of events long past. The challenge is learning how to read them. Perhaps the most important piece of evidence arrived almost by accident. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Telephone Laboratories in New Jersey. Their instrument was an exquisitely sensitive horn antenna designed for satellite communication experiments. Instead of perfect silence, they detected a faint microwave signal. It seemed to come from every direction. At first, they suspected their equipment. They examined the electronics. They checked nearby radio interference. They even removed pigeons nesting inside the antenna and cleaned away what they politely described as white dielectric material. The mysterious noise remained. Unknown to them, another group of physicists at nearby Princeton University had been searching for exactly such a signal. Years earlier, theoretical work by George Gamow, Ralph Alpher and Robert Herman had suggested that if the universe began in an extremely hot, dense state, it should still contain a faint glow left over from that early epoch. As the universe expanded, that ancient light would gradually cool. Billions of years later, it should survive as microwave radiation filling all of space. Penzias and Wilson had unknowingly discovered it. Today we call it the cosmic microwave background, often shortened to the CMB. It represents the oldest light that can be observed directly. Before its release, the universe was so hot that electrons and atomic nuclei existed in a dense plasma. Photons constantly scattered from charged particles, making the young cosmos opaque. About 380,000 years after the beginning of cosmic expansion, temperatures fell enough for electrons and nuclei to combine into neutral atoms. Suddenly, light could travel freely. Those photons have been crossing the universe ever since. Every time astronomers observe the CMB, they are detecting radiation that has journeyed for nearly the entire age of the cosmos. Its importance cannot be overstated. If the universe possessed a preferred center or a strongly preferred direction, that ancient light might reasonably be expected to reveal it. Instead, the microwave background is astonishingly uniform. Across the entire sky, its temperature averages about 2.725 Kelvin, only a few degrees above absolute zero. The variations are extraordinarily small. Most differ by only about 1 part in 100,000. To appreciate this level of uniformity, consider the Earth's surface. Temperatures vary by tens of degrees between continents. Mountains, oceans, deserts, and forests all create enormous differences. The early observable universe, by comparison, was remarkably smooth. Yet those tiny variations are precisely what make our existence possible. Had the microwave background been perfectly uniform, gravity would have possessed no slightly denser regions upon which to act. Galaxies would never have formed, stars would never have ignited, planets, oceans, and living organisms would almost certainly never have appeared. Those minute fluctuations became the seeds from which all later cosmic structure grew. Modern satellites have measured them with extraordinary precision. NASA's COBE satellite first confirmed their existence in 1992. Later missions, including WMAP and the European Space Agency's Planck spacecraft, mapped the temperature variations across the entire sky in remarkable detail. These observations transformed cosmology into a precision science. The microwave background does contain one particularly noticeable asymmetry. One side of the sky appears ever so slightly warmer. The opposite side appears slightly cooler. At first glance, this might seem to suggest a preferred cosmic direction. In reality, astronomers interpret this feature quite differently. The effect arises because our solar system is moving through space. As we travel relative to the microwave background, radiation arriving from the direction of motion is compressed slightly, increasing its measured temperature. Radiation arriving from behind is stretched slightly, lowering its temperature. This phenomenon, called the CMB dipole, is analogous to the Doppler effect already discussed for galaxies. After correcting for this motion, the remarkable uniformity returns. Far from revealing a cosmic center, the microwave background reinforces the conclusion that the observable universe appears statistically similar in every direction. Of course, one line of evidence is never enough. Astronomers therefore turned to another. If galaxies truly evolved from the tiny fluctuations observed in the microwave background, then their present-day distribution should preserve a predictable pattern. This is where modern galaxy surveys become indispensable. Jets such as the Sloan Digital Sky Survey and later international collaborations have mapped the positions of millions of galaxies across enormous volumes of space. Each galaxy contributes a single point. Together they reveal one of the largest maps humanity has ever constructed. From nearby galaxies only a few million light-years away to systems whose light has traveled billions of years before reaching Earth, these surveys chart the cosmic web in breathtaking detail. Filaments stretch across hundreds of millions of light-years. Clusters gather at their intersections. Immense voids occupy the spaces between. The structures appear complex, yet statistical analysis once again tells a familiar story. No large-scale preferred direction emerges. No region behaves as though everything expands away from it. The average properties remain strikingly consistent across the observable cosmos. Another independent measurement reaches the same conclusion. Astronomers study a feature known as baryon acoustic oscillations. The name sounds technical, but the idea begins with sound waves. In the first few 100,000 years after cosmic expansion began, ordinary matter and radiation formed a hot, dense plasma. Pressure waves traveled through this plasma much as sound waves move through air. When neutral atoms eventually formed and light began traveling freely, Those waves effectively froze into the distribution of matter. Billions of years later, their imprint remains detectable in the spacing between galaxies. These ancient acoustic patterns act as a kind of cosmic ruler. By measuring them across different epochs, astronomers can reconstruct how the universe has expanded over time. Once again, the observations agree remarkably well with models assuming large-scale homogeneity and isotropy. The evidence does not end there. Gravitational lensing allows astronomers to map invisible concentrations of matter. The abundances of hydrogen and helium preserve information about conditions in the early universe. Galaxy clusters reveal the growth of structure across cosmic history. Each method relies upon different physical principles. Each contains different systematic uncertainties, yet they converge upon a remarkably consistent picture. This convergence is perhaps the strongest argument in modern cosmology. No single observation proves that the universe lacks a center. Instead, many independent observations all point toward the same conclusion. Science gains confidence not because one experiment is flawless, but because entirely different approaches repeatedly reinforce one another. Still, careful scientists remain cautious. Evidence always has limits. The observable universe, vast though it is, may represent only a small portion of the entire cosmos. Beyond our cosmic horizon, direct measurements becomes impossible. There could exist structures so enormous that we cannot yet perceive them. There could be geometrical features extending far beyond the observable limit. Current observations neither confirm nor exclude every conceivable possibility. What they do tell us is narrower, but immensely powerful. Within everything humanity has been able to observe, no evidence requires a unique cosmic center. Yet observations alone cannot explain why this is so. To answer that question, cosmologists have proposed several competing descriptions of the universe itself. Some differ only subtly, others envision radically different geometries. Each attempts to account for the same evidence, and each carries its own strengths, assumptions, and unanswered questions. The remarkable consistency of modern observations leaves cosmologists with an unusual challenge. The evidence is abundant. The measurements have become increasingly precise. Yet more than one theoretical picture can account for many of those observations. This is a normal part of science. Observations provide constraints. Theories attempt to explain them. As new evidence arrives, some ideas become stronger, others weaker, and a few are eventually abandoned altogether. The search for the center of the universe illustrates this process particularly well, because it depends not only upon what astronomers observe, but also upon how they interpret the geometry of the cosmos. Before comparing competing ideas, it is helpful to separate several different categories that are often blended together in popular discussions. An observed fact is something directly measured. Galaxies exhibit redshifts. The cosmic microwave background exists. The large-scale distribution of galaxies can be mapped. These observations are independent of any single cosmological model. An accepted theory is a framework that successfully explains a wide range of observations and has survived extensive testing. General relativity belongs in this category. So does the standard model of cosmology, often called the lambda cold dark matter model, or lambda CDM. A hypothesis is a scientifically motivated proposal that has not yet received sufficient confirmation. Many ideas concerning the earliest moments of cosmic history fall into this category. Finally, speculation refers to possibilities that may be mathematically interesting or philosophically appealing, but currently lack observational support. Keeping these distinctions clear allows scientists to discuss uncertainty without confusing it with disagreement over established evidence. The most widely accepted cosmological framework today is the LAM-CDM model. Despite its complicated name, its foundations are surprisingly straightforward. The universe expands. Ordinary matter forms stars, planets, and galaxies. Invisible dark matter provides additional gravity that helps cosmic structures grow. Dark energy drives the accelerated expansion observed today. General relativity governs the behavior of spacetime on the largest scales. Within this framework, no preferred center exists. Every sufficiently large region follows the same physical laws. The model has enjoyed extraordinary success because it explains an impressive range of observations simultaneously. It predicts the large-scale structure of galaxies. It reproduces the temperature fluctuations observed in the cosmic microwave background. It accounts for the abundances of light elements produced during the first few minutes of cosmic history. It successfully describes gravitational lensing, galaxy clustering, and the expansion history inferred from distant supernovae. No competing model currently matches this breadth of agreement as consistently. That does not mean Lambda CDM is complete. In fact, two of its most important ingredients remain mysterious. Dark matter has never been detected directly, despite decades of experimental searches. Dark energy, which appears to dominate the present-day energy content of the universe, has an unknown physical origin. The model works remarkably well, yet part of what it describes remains unidentified. Science sometimes progresses in exactly this way. Newton accurately described gravity centuries before its deeper explanation emerged through Einstein's relativity. A successful theory need not answer every question immediately. Still, cosmologists continue exploring alternatives. One possibility concerns the overall shape of space itself. Many people unconsciously picture the universe as infinite, because it seems easier to imagine endless space than a finite cosmos. Yet modern cosmology does not require infinity. Current observations are compatible with several possibilities. The universe could be spatially infinite. It could also be finite but unbounded. This second idea often surprises people. How can something possess finite size without having an edge? The answer comes from geometry. Consider the two-dimensional surface of Earth. Its area is finite. A traveler can continue walking indefinitely without encountering a boundary. Eventually, they return to their starting point. The surface possesses no edge despite enclosing a limited area. Some cosmological models describe three-dimensional space in an analogous way. If our universe has positive curvature on sufficiently large scales, traveling far enough in one direction might theoretically bring an observer back to their point of origin, although current observations suggest that if such curvature exists, it is extremely small. In either case, finite or infinite, a unique center does not necessarily follow. A sphere's surface has no privileged point. Every location is equally valid. The center of the sphere exists only in a higher dimensional space that forms part of the mathematical description, not as a location accessible to beings living solely upon the surface. Cosmologists emphasize this distinction carefully because it is easy to misunderstand. Another class of ideas concerns cosmic topology. Geometry describes local curvature. Topology describes global connectedness. Two spaces may possess identical local geometry, while differing dramatically in their overall structure. Some speculative models propose that the universe could wrap around itself in subtle ways. Light traveling far enough might eventually return from another direction, potentially allowing astronomers to observe multiple images of the same distant galaxy. Extensive searches have sought evidence for such patterns within the cosmic microwave background. So far, none has provided convincing confirmation. These ideas therefore remain interesting hypotheses rather than accepted descriptions. There are also models that deliberately abandon the cosmological principle. Some propose that the observable universe occupies an unusually large cosmic void. If true, the apparent acceleration of cosmic expansion might arise partly from our position within this underdense region rather than from dark energy itself. Such models attracted considerable attention after the discovery of accelerating expansion in the late 1990s. However, increasingly precise observations have placed strong constraints upon them. To reproduce the data successfully, these voids would need to possess very specific properties while remaining consistent with measurements of the cosmic microwave background, galaxy surveys, and supernova distances. Most cosmologists therefore regard them as considerably less successful than Lambda CDM, although aspects of these ideas continue to be investigated. Another important distinction concerns inflation. Inflation is not an alternative to the standard cosmological model. Rather, it is a proposed extension describing an extremely brief period of rapid expansion during the earliest fraction of a second. Inflation helps explain why distant regions of the observable universe possess nearly identical temperatures, despite being separated by enormous distances today. It also predicts the nearly scale-invariant pattern of tiny fluctuations later observed in the cosmic microwave background. Many observations support inflation's general predictions. Yet important questions remain. Physicists still debate the detailed mechanism responsible. Different inflationary models make subtly different predictions. Future observations may distinguish among them. Inflation itself does not introduce a cosmic center. Indeed, many versions strengthen the expectation that no preferred location exists. Some speculative extensions even suggest that inflation could continue indefinitely in distant regions, producing what is sometimes called eternal inflation. Within this framework, our observable universe would represent only one region embedded within a much larger inflating spacetime. It is important to pause here. Eternal inflation remains speculative. It has not been confirmed observationally. Its mathematical foundations are actively studied, but its broader implications remain uncertain. It should not be confused with established cosmological fact. An even more speculative collection of ideas concerns the multiverse. Various branches of theoretical physics have proposed scenarios in which multiple universes might exist. Some emerge from eternal inflation. Others arise from interpretations of quantum mechanics or string theory. These concepts receive considerable public attention. Yet, with respect to the question guiding our journey, they currently offer little observational guidance. No direct evidence confirms the existence of other universes. Consequently, they occupy the frontier between theoretical exploration and philosophical possibility. Modern cosmology neither accepts nor rejects them as established reality. It simply acknowledges that present observations remain insufficient. One feature unites nearly all successful cosmological models, whether space is finite or infinite, whether inflation occurred or did not, whether dark energy ultimately proves to be a cosmological constant or something more complex. The observable evidence consistently favors a universe lacking any detectable preferred location, not because scientists insist upon that conclusion, because every increasingly precise measurement continues to point in that direction. Yet there remains one final way to examine the problem. Rather than beginning with observations and asking which theory explains them, we can reverse the question entirely. Suppose, for a moment, that intuition were correct. Suppose the universe really did possess a genuine center. What would astronomers actually expect to see, and how different would our night sky become from the one we observe today? One of the most useful tools in science is the thought experiment. Unlike speculation, a scientific thought experiment begins with established physics. It temporarily assumes that a particular idea is true, then carefully follows its consequences. If those consequences agree with observation, the idea survives another test. If they contradict reality, the idea becomes less likely. The search for the center of the universe invites exactly this kind of exercise. Let us suppose, for the moment, that there really is a unique location from which the entire universe expanded. Not merely a point in the distant past, but a genuine center that still exists within the geometry of the cosmos today. If that assumption were correct, what would astronomers expect to observe? The first consequence concerns motion. Consider an ordinary explosion on Earth. Fragments nearest the center move outward in every direction. Every piece carries a velocity that depends upon the explosion itself. But the geometry remains straightforward. There is one privileged location from which every trajectory originates. Now imagine living far away from that center. Objects on one side of the sky would generally be moving differently from objects on the opposite side. The overall expansion would possess an unmistakable directional character. An observer located exactly at the center would experience perfect symmetry. An observer displaced from that center would not. This is an unavoidable consequence of ordinary geometry. The farther one travels away from the central point, the easier it becomes to determine its direction. Astronomers have spent decades searching for precisely such large-scale asymmetries. They have examined the motions of galaxies. They have mapped the distribution of galaxy clusters. They have measured the cosmic microwave background with extraordinary precision. So far, no observation has revealed the kind of directional pattern expected from a universe expanding away from a single location embedded within space. That does not prove such a center is impossible. Science rarely proves universal negatives. It does mean that if such a center exists, it leaves no measurable signature within the observable universe consistent with our current observations. The second consequence concerns density. Imagine again an ordinary explosion. Material near the center initially occupies a denser region than material much farther away. Even after long periods of expansion, traces of that original gradient often remain. Applied to cosmology, a genuine center might produce systematic changes in the average distribution of galaxies. Perhaps one direction would contain progressively older galaxies. Perhaps matter would become steadily denser toward one region of space. Perhaps the rate of cosmic expansion would vary depending upon where observations were made. Extensive galaxy surveys have searched for these possibilities. Instead, the average properties of the observable universe remained remarkably consistent over enormous distances. Local differences certainly exist. Some regions contain rich galaxy clusters. Others consist largely of vast cosmic voids. Yet once observations average over hundreds of millions of light-years, those variations begin to smooth away. No global density gradient pointing toward a central location has emerged. The third consequence involves the oldest light in the universe. If a unique center existed, the cosmic microwave background would likely preserve some memory of it. After all, that ancient radiation originated when the universe was only about 380,000 years old. If one direction corresponded to a fundamentally different position within the expanding cosmos, subtle temperature differences might naturally arise across the sky instead. After accounting for our own motion through space, the microwave background remains extraordinarily uniform. Its tiny fluctuations match the statistical properties predicted by the standard cosmological model with remarkable accuracy. The absence of a preferred direction is one of the strongest observational arguments against a detectable cosmic center. There is another, more subtle prediction. Suppose intelligent astronomers lived inside a galaxy billions of light years away. If the universe possessed a true center, their observations should differ significantly from ours. Depending upon their location relative to that center, they would measure different large-scale recession patterns. Some directions might contain galaxies approaching rather than receding. Other directions might exhibit noticeably different expansion rates. Yet according to the standard cosmological framework, observers almost anywhere in the observable universe would describe remarkably similar large-scale behavior. Each would see distant galaxies generally moving away. Each would detect a cosmic microwave background surrounding them. Each would construct an observable universe centered upon their own location. This is one of the most counterintuitive consequences of expanding space. Every observer naturally appears to occupy the middle of their observable cosmos, not because they are special, because light requires time to travel. Every observer is surrounded by a horizon defined by the age of the universe and the finite speed of light. These horizons overlap, intersect, and differ slightly depending upon location. Yet none identifies a universal center. It is tempting to ask a different question. If the universe has no center, could it at least have an edge again? Everyday intuition suggests that one should accompany the other. A table has edges because it has a finite extent. A lake has a shoreline because water ends somewhere. If the universe lacks an edge, does that automatically imply infinity? Surprisingly, the answer is no. Geometry once again offers possibilities unfamiliar from ordinary experience. As discussed earlier, a space may be finite without possessing boundaries. Modern observations indicate that if the universe is spatially curved, that curvature is extremely close to flat. Current measurements are consistent with a universe that is either truly infinite or so enormously large that any overall curvature lies far beyond the limits of the observable cosmos. At present, astronomers cannot distinguish conclusively between these possibilities. This uncertainty highlights an important feature of scientific reasoning. Sometimes multiple models remain compatible with existing evidence, rather than choosing among them by preference. Scientists acknowledge the uncertainty and continue searching for observations capable of discriminating between them. The absence of a detectable center, therefore, does not automatically answer every geometrical question. It simply narrows the possibilities. There is one final thought experiment worth considering. Suppose, instead of asking where the center is, we ask whether the concept itself belongs to the wrong category. Centuries ago, people searched for the place where Earth ended and the heavens began. They imagined a literal boundary separating two different realms. As knowledge advanced, that question gradually lost its meaning. There is no physical ceiling enclosing the atmosphere. The distinction between Earth and space becomes a gradual transition rather than a sharp line. Perhaps the search for the center of the universe reflects a similar misunderstanding. Perhaps the geometry described by general relativity does not require such a location any more than Earth's atmosphere requires a visible edge. If so, Humanity has spent generations searching for something that the universe never promised to contain. That possibility is not a philosophical surrender. It is a scientific conclusion emerging from decades of increasingly precise observation. Yet it carries consequences extending far beyond geometry. If no privileged location exists, then every galaxy, every cluster, and every observer participates equally in the expansion of the cosmos. The mystery is no longer about finding one special place. It becomes about understanding the nature of space itself. And once attention shifts from location to spacetime, the question reaches outward into the largest structures known to science. Dark matter, dark energy, gravity, the evolution of galaxies, and the fate of the universe all become part of the same story. The search for a center quietly transforms into something even larger. It becomes a search for the rules governing the cosmos itself. By the time astronomers concluded that the observable universe shows no evidence of a unique center, they had unknowingly stepped into a much larger investigation. The question was no longer confined to geometry. It now reached into nearly every major branch of cosmology. Understanding why no center can be identified requires understanding how the largest structures in the universe formed, how gravity shaped them across billions of years, and why the expansion of space itself continues to evolve. These subjects may appear separate at first glance. Galaxies belong to one field. Dark matter belongs to another. Dark energy seems to occupy an entirely different corner of modern physics. Yet each becomes part of the same cosmic narrative once we ask how the universe changes on the largest possible scales. The story begins shortly after the release of the cosmic microwave background. At that time, the universe was remarkably smooth. The tiny variations in density, measured by satellites such as COBE, WMAP, and Planck, amounted to only a few parts in 100,000. Those fluctuations were far too small to resemble today's immense galaxy clusters. Something had to amplify them. That something was gravity. Over hundreds of millions of years, slightly denser regions attracted additional matter. As they became more massive, their gravitational pulls strengthened. More matter accumulated. The process repeated itself again and again. This gradual growth is known as gravitational instability. It is one of the fundamental mechanisms by which simple beginnings produced the richly structured cosmos we observe today. Computer simulations have become one of astronomy's most powerful tools for studying this process. Researchers begin by constructing a virtual universe whose initial conditions closely match the tiny fluctuations observed in the cosmic microwave background. They then allow gravity to operate over billions of simulated years. The results are striking. Filaments emerge. Galaxy clusters gather at their intersections. Immense voids open between them. Without programming these structures directly, the simulations naturally produce a cosmic web resembling the one revealed by modern galaxy surveys. This agreement represents one of the strongest successes of contemporary cosmology. The simulations do not reproduce every detail perfectly. Small-scale discrepancies remain under active investigation. Nevertheless, the broad correspondence between prediction and observation is remarkable. Yet another mystery soon appeared. When astronomers compared the visible matter inside galaxies with the motions of their stars, something refused to fit. According to Newtonian gravity and later general relativity, stars farther from a galaxy's center should orbit more slowly once most of the visible mass lies inside their orbit. Instead, observations revealed nearly flat rotation curves. Stars at enormous distances continued orbiting unexpectedly fast. The galaxies behaved as though far more matter existed than telescopes could see. This invisible component became known as dark matter. The name describes what astronomers observe rather than what dark matter actually is. It appears to interact gravitationally. It neither emits nor reflects detectable light. Despite decades of research, its underlying nature remains unknown. Several possibilities have been proposed. Some physicists search for new elementary particles. Others investigate modifications of gravity itself. Numerous experiments continue worldwide. So far, none has provided a definitive answer, regardless of its identity. Dark matter plays a central role in the growth of cosmic structure. Ordinary matter interacts with light. During the early universe, radiation pressure resisted gravitational collapse. Dark matter, however, appears largely unaffected by light. It could therefore begin gathering into dense regions earlier, creating gravitational wells into which ordinary matter later fell. Without this invisible framework, the galaxies observed today would have struggled to form within the available cosmic time. In this sense, the visible universe may be only the illuminated surface of a much larger gravitational architecture. Again, the question of a cosmic center quietly recedes. Dark matter does not gather around one privileged location. Its distribution follows the same large-scale statistical uniformity seen in ordinary matter. The cosmic web extends everywhere astronomers can observe. Then, just as cosmologists began constructing a coherent picture of structure formation, another surprise emerged. During the late 20th century, two independent teams of astronomers studied distant Type 1a supernovae. These stellar explosions possess remarkably consistent intrinsic brightness, allowing them to serve as standard candles across cosmological distances. The researchers hoped to measure how rapidly cosmic expansion had slowed under the influence of gravity. Instead, they discovered something unexpected. The expansion of the universe is accelerating. Galaxies continue separating from one another at an increasing rate. The observation did not imply that individual galaxies themselves accelerate through space like rockets. Rather, the scale of space between sufficiently distant galaxies grows ever more rapidly. To account for this behavior, cosmologists revived an idea that Einstein himself had once introduced for entirely different reasons: the cosmological constant. In modern cosmology, the simplest interpretation associates this constant with dark energy, a mysterious component that appears to permeate space itself. Dark energy currently dominates the energy budget of the universe, yet its physical origin remains one of the deepest unsolved problems in theoretical physics. Its measured value is astonishingly small compared with many predictions arising from quantum field theory. No widely accepted explanation has resolved this discrepancy. Still, observations consistently indicate that something very much like dark energy influences cosmic expansion. Its effects become significant only across enormous distances. Within galaxies, gravity easily overwhelms them. Galaxy clusters remain gravitationally bound. The solar system experiences no measurable influence. Only when considering the universe on its largest scales does dark energy gradually dominate the overall dynamics. This distinction is important. Expansion does not pull apart planets. It does not stretch people. It does not tear apart galaxies. Local gravity, electromagnetic forces, and even molecular bonds are vastly stronger than cosmic expansion across those scales. The universe expands primarily in the immense regions separating galaxy clusters. As space grows, another consequence follows. The observable universe changes. Light emitted today by sufficiently distant galaxies may never reach us if expansion carries those galaxies away rapidly enough. Conversely, some light now arriving began its journey when those galaxies were considerably closer than they appear today. Cosmic history becomes a dialogue between light and expansion. What we observe depends not only upon where objects are, but also upon how the geometry of space-time has evolved while their light traveled. This dynamic picture makes the search for a center increasingly difficult. There is no fixed stage upon which galaxies move. The stage itself changes continuously. Distances evolve. Horizons evolve. Even the portion of the universe accessible to observation evolves. The largest structures known to science therefore tell a remarkably consistent story. Gravity builds complexity. Dark matter provides invisible scaffolding. Dark energy influences the long-term expansion of spacetime. Galaxies gather into clusters, filaments, and walls. Yet nowhere within this grand architecture does a unique center emerge. Instead, every discovery reinforces a more subtle idea. The universe is not organized around one privileged place. It is organized by universal physical laws operating everywhere that observations have been able to reach. Still, this conclusion invites one final, deeper realization. Many of these discoveries were made independently. The cosmic microwave background, galaxy surveys, gravitational lensing, dark matter, dark energy, general relativity. Each began as its own scientific puzzle. Only gradually did astronomers recognize that they were all pointing toward the same underlying picture of the cosmos. The next step in our journey is to uncover those unexpected connections and see how seemingly unrelated discoveries quietly reinforce one another, revealing a universe more coherent and perhaps more mysterious than any single observation could have suggested. One of the most satisfying moments in science comes when discoveries made decades apart by different researchers using entirely different instruments begin to fit together like pieces of the same puzzle. No single observation reveals the whole picture. Instead, each contributes a fragment, a faint glow detected by a radio antenna, a distant galaxy distorted by gravity, a map containing millions of galaxies, a subtle ripple frozen into the oldest light in the universe. Viewed individually, these discoveries answer specific questions. Viewed together, they reveal something much larger. The absence of a detectable center in the universe is not supported by one extraordinary measurement. It emerges because many independent branches of astronomy, developed for entirely different purposes, quietly converge on the same conclusion. Consider gravitational lensing. Einstein's theory of general relativity predicts that mass bends spacetime, causing light to follow curved paths. When light from a distant galaxy passes near a massive cluster of galaxies, its path is deflected. To observers on Earth, the distant galaxy may appear stretched, magnified, or even duplicated into multiple images. These cosmic lenses serve two remarkable purposes. First, they allow astronomers to study galaxies that would otherwise be too faint to observe. Second, and perhaps even more importantly, they reveal the distribution of mass itself. Visible matter alone cannot account for the amount of bending that astronomers measure. Once again, invisible dark matter appears. By mapping thousands of gravitational lenses across the sky, researchers have reconstructed enormous dark matter structures, extending through galaxy clusters and filaments. These maps were never designed to answer questions about the center of the universe, yet they do so indirectly. The gravitational scaffolding appears statistically consistent with the same large-scale homogeneity revealed by galaxy surveys and the cosmic microwave background. Another connection emerges through the growth of galaxy clusters. Clusters are among the largest gravitationally bound objects in existence. Some contain thousands of galaxies immersed in enormous clouds of hot gas, emitting powerful X-rays. They also contain vast quantities of dark matter. The number of galaxy clusters changes over cosmic time. By measuring their abundance at different distances, astronomers can trace how rapidly cosmic structures formed. Remarkably, these measurements agree with conclusions drawn from completely different techniques. The rate at which galaxy clusters grow matches the expectations derived from the tiny temperature fluctuations in the cosmic microwave background. Provided that dark matter and dark energy are included in the model, the universe appears to tell the same story twice, once through its earliest light, again through its largest structures billions of years later. The connection is extraordinary because these observations are separated by almost the entire age of cosmic history. The microwave background shows the universe when it was only 380,000 years old. Galaxy clusters reveal it after more than 13 billion years of evolution. Between those two moments lies nearly the entire history of stars, galaxies, planets, and life itself. Yet the underlying pattern remains consistent. This consistency gives cosmologists confidence that they are not merely fitting isolated observations. They are uncovering a coherent physical history. Another unexpected bridge connects geometry with time. Every observation made by an astronomer is also an observation of the past. Light does not travel instantaneously. The moon appears as it was about 1¼ seconds ago. Sunlight requires approximately 8 minutes to reach Earth. The light from the Andromeda galaxy began its journey roughly 2.5 million years ago. The most distant galaxies visible to modern telescopes appear as they existed only a few 100 million years after the beginning of cosmic expansion. Astronomy, therefore, possesses a remarkable advantage unavailable to most sciences. Looking farther into space automatically means looking farther back in time. The observable universe functions as a vast historical archive. Instead of excavating ancient rocks, astronomers excavate ancient light. This relationship between distance and time also explains why the search for a cosmic center cannot rely upon a simple map. A three-dimensional map of galaxies is never a snapshot of one single moment. Nearby galaxies appear relatively old in cosmic terms. More distant galaxies appear progressively younger. The farthest observable objects belong to an era when the first generations of stars had only recently formed. Every direction contains multiple epochs layered together. The universe resembles a history book whose pages are arranged according to distance. This complicates every attempt to infer its overall geometry. Cosmologists must account not only for where galaxies are, but also for when their light was emitted. Another surprising connection involves black holes. At first glance, black holes seem entirely unrelated to the question of whether the universe possesses a center. They are local objects. Some form from collapsing stars. Others grow into supermassive black holes, occupying the centers of galaxies. Yet black holes provide some of the strongest tests of general relativity. The same theory that predicts how matter behaves near an event horizon also predicts how spacetime evolves across the entire observable universe. Measurements of stars orbiting Sagittarius A star at the center of the Milky Way, images of the black hole in the galaxy M87, and the detection of gravitational waves from merging black holes all reinforce the remarkable accuracy of Einstein's theory under vastly different conditions. One theory successfully describes gravity from the scale of stellar remnants to the evolution of the cosmos itself. This unity is one of modern physics' greatest achievements. Gravitational waves provide another unexpected connection. First directly detected in 2015 by the LIGO observatories, these tiny ripples in spacetime arise when massive objects, such as black holes or neutron stars, accelerate violently. Their detection opened an entirely new way of observing the universe. Unlike light, gravitational waves pass almost unhindered through matter. Future detectors may eventually observe signals originating much earlier in cosmic history than electromagnetic telescopes can reach. Some proposed observatories hope to detect gravitational waves associated with processes occurring fractions of a second after cosmic expansion began. If successful, these observations could provide entirely new tests of inflation and the earliest evolution of space-time. Although they are unlikely to reveal a literal center, they may greatly improve our understanding of the conditions that shaped the young universe. There is another connection that often goes unnoticed. The same physical laws appear to operate everywhere astronomers have been able to observe. The spectral fingerprints of hydrogen, helium, oxygen, carbon, and countless other elements remain the same across billions of light years. Gravity behaves consistently. Atomic physics remains unchanged. The speed of light appears constant. If the universe possessed fundamentally different regions governed by different laws, astronomers might expect subtle departures from these patterns. So far, observations have found remarkable consistency. This does not prove that conditions beyond the observable horizon are identical. Science cannot currently test regions forever hidden from view. It does mean that within everything humanity has observed, nature displays a striking degree of unity. Perhaps the most profound connection of all concerns perspective. Every major discovery discussed throughout this journey gradually removed another privileged position. Earth is not the center of the solar system. The Sun is not the center of the Milky Way. The Milky Way is not the center of the observable cosmos. Even the observable universe itself is centered only because every observer necessarily views reality from their own location. The pattern is unmistakable. As knowledge has expanded, the universe has become less centered on us and more governed by universal principles. This realization does not diminish humanity's place within the cosmos. If anything, it elevates the achievement of understanding. From a small planet orbiting an ordinary star in one spiral arm of one ordinary galaxy, intelligent beings have learned to reconstruct the history of nearly the entire observable universe using nothing more than light, mathematics, careful measurement, and patient curiosity. Yet every new instrument has revealed not only greater clarity, but also deeper uncertainty. The more precisely astronomers map the cosmos, the more subtle the remaining questions become. The search for the center has largely transformed into a search for the limits of our understanding, and those limits are now being explored by an extraordinary new generation of observatories, spacecraft, surveys, and simulations that are beginning to examine the universe with unprecedented precision. Modern astronomy has entered an era unlike any before it. For most of history, a single telescope represented the height of observational technology. One astronomer, one instrument, and one portion of the sky were often enough to produce discoveries that reshaped humanity's understanding of the cosmos. Today, the picture is very different. The universe is observed simultaneously by spacecraft orbiting Earth, telescopes resting upon remote mountaintops, radio dishes spread across continents, detectors buried deep underground, and supercomputers capable of simulating billions of years of cosmic evolution. Each instrument sees a different universe. Visible light reveals stars. Infrared light penetrates clouds of dust. Radio waves expose cold hydrogen drifting between galaxies. X-rays uncover matter heated to millions of degrees. Gravitational waves carry information from violent events invisible to ordinary telescopes. Together, they create a far richer picture than any single observation could provide. One of the clearest examples of this new approach is the James Webb Space Telescope. Positioned nearly 1.5 million kilometers from Earth, near the second Sun-Earth Lagrange point. Webb observes primarily in infrared wavelengths. Its large mirror and exceptional sensitivity allow it to detect galaxies whose light has traveled for more than 13 billion years. These are not necessarily the first galaxies ever to exist. Rather, they are among the earliest that current technology can observe directly. Their importance extends far beyond simply finding distant objects. Every newly discovered early galaxy provides another test of cosmological models. How quickly did the first stars form? How rapidly did galaxies assemble? How much dark matter must have existed to produce these structures? Each observation either strengthens existing theories or forces them to be refined. In its first years of operation, Webb revealed surprisingly mature galaxies existing earlier than many astronomers expected. These discoveries generated considerable discussion within the scientific community. Importantly, they did not overturn modern cosmology. Instead, they prompted researchers to re-examine assumptions about star formation, galaxy evolution, and observational interpretation. This illustrates an essential feature of science. Unexpected observations do not immediately invalidate successful theories. Rather, they encourage careful investigation until the evidence becomes sufficiently clear, while Webb explores the distant past. Other observatories examine the nearby universe in extraordinary detail. The European Space Agency's Gaia spacecraft has transformed our understanding of the Milky Way. Rather than observing distant galaxies, Gaia measures the positions, motions, and distances of more than 1 billion stars. Its precision is astonishing. For many nearby stars, positional measurements correspond to detecting an angle comparable to the width of a human hair, viewed from thousands of kilometers away. These observations allow astronomers to reconstruct the three-dimensional structure of our galaxy with unprecedented accuracy. They reveal ancient stellar streams left behind by galaxies that merged with the Milky Way billions of years ago. They uncover subtle motions within the galactic disk. They improve the calibration of the cosmic distance ladder upon which much of observational cosmology depends. While Gaia does not search directly for the center of the universe, it strengthens one of the foundations supporting modern cosmology. Better local measurements improve the accuracy of measurements across the observable cosmos. Elsewhere, enormous galaxy surveys continue expanding humanity's largest maps. Projects such as the Dark Energy Survey have charted hundreds of millions of galaxies while studying how cosmic structure has evolved over billions of years. Newer facilities promise even greater precision. The Vera C. Rubin Observatory, equipped with one of the largest digital cameras ever constructed for astronomy, is designed to repeatedly image the entire southern sky over many years. Rather than producing a single static map, it will create a dynamic record of billions of celestial objects. Asteroids will move. Supernovae will appear and fade. Variable stars will brighten and dim. Galaxies will accumulate into an archive of extraordinary depth. This immense dataset will help astronomers investigate dark matter, dark energy, gravitational lensing, and the growth of cosmic structure with unprecedented statistical power. The search for a cosmic center may not be its primary objective. Nevertheless, every improvement in measuring the large-scale distribution of matter provides another opportunity to test whether the universe truly remains homogeneous and isotropic on the greatest observable scales. Radio astronomy has entered a similar period of transformation. The Square Kilometre Array, now under construction across Australia and South Africa, will eventually become the largest radio observatory ever built. Its enormous collecting area will allow astronomers to map hydrogen gas across vast regions of cosmic history. Hydrogen is the most abundant element in the universe. Tracing its distribution means tracing the evolution of matter itself. These observations may reveal how galaxies formed within the expanding cosmic web and how large-scale structures evolved over billions of years. Meanwhile, another entirely different field continues developing: Gravitational wave astronomy is still in its infancy. The first direct detection by LIGO in 2015 confirmed a prediction Einstein had made a century earlier. Since then, dozens of mergers involving black holes and neutron stars have been observed. Future detectors promise dramatically greater sensitivity. The European Space Agency's planned Laser Interferometer Space Antenna, or LISA, will place 3 spacecraft millions of kilometers apart, creating a detector capable of observing much lower frequency gravitational waves than ground-based observatories. These signals originate from supermassive black holes, compact binary systems, and potentially from processes occurring in the very early universe. If primordial gravitational waves are eventually detected, they could provide one of the strongest observational tests of inflation. Such measurements would not reveal the center of the universe. They could, however, illuminate conditions existing far earlier than any electromagnetic telescope can observe. Computer simulations have advanced just as rapidly. Modern cosmological simulations now model enormous volumes of the universe containing billions of particles representing dark matter and black holes. Programs such as Illustris TNG and Millennium simulate billions of years of cosmic evolution using the known laws of physics. Their purpose is not merely to create beautiful images. Researchers compare simulated universes with real observations. Do galaxy clusters form at the correct rate? Do spiral galaxies resemble those actually observed? Does the cosmic web possess the expected statistical properties? Agreement builds confidence. Disagreement identifies areas requiring improvement. In many ways, simulations function as laboratories for cosmology. Scientists cannot rerun the real universe. They can rerun virtual ones. By adjusting assumptions and comparing outcomes with observation, they gradually narrow the range of viable explanations. Yet even the most sophisticated simulations remain incomplete. They rely upon approximations. Some physical processes occur on scales too small to calculate directly. Others involve phenomena whose underlying physics remains uncertain. Every simulation, therefore, reflects both what scientists know and what they still hope to understand. One of the most exciting developments of recent years has been the increasing convergence of these diverse approaches. A distant galaxy discovered by Webb can be compared with predictions from numerical simulations. Its mass distribution can be studied through gravitational lensing. Its surrounding hydrogen can be mapped using radio observations. Its environment can be incorporated into large galaxy surveys. Different instruments, operating across different wavelengths, contribute pieces of the same investigation. This coordinated approach has dramatically increased confidence in many aspects of modern cosmology. At the same time, it has revealed that some of the most important questions remain stubbornly unanswered. The more precisely astronomers measure the universe, the more clearly they perceive the limits of current knowledge. Dark matter remains unidentified. Dark energy remains unexplained. The earliest fraction of a second after cosmic expansion began remains hidden from direct observation. The overall size of the universe remains uncertain. Whether space is truly infinite or simply far larger than the observable horizon remains unknown. The search for the center has therefore reached an unexpected destination, rather than discovering a hidden point in space. Modern astronomy has uncovered the boundaries of observation itself. Beyond those boundaries lies not certainty, but carefully defined uncertainty. And understanding those limits may ultimately prove just as important as any discovery already made. There is a quiet moment in every scientific journey when the excitement of discovery gives way to something deeper. The instruments become more powerful, the measurements become more precise, the maps become more detailed, and yet, instead of the universe becoming simple, it becomes more mysterious. The search for the center of the cosmos has reached exactly this point. Humanity has learned more about the structure of the universe than any previous civilization could have imagined. We know that galaxies are separated by expanding space. We know that the cosmos has evolved from a hotter, denser early state. We know that the large-scale universe appears remarkably uniform. We know that no observation has revealed a unique location that can be called the center. But science is not defined only by what is known. It is equally defined by recognizing what remains uncertain. And in cosmology, those uncertainties are among the most profound questions ever asked. The first limitation is observational. The universe has an observable boundary. This boundary is not an edge of space. It is an edge of information. Light travels at a finite speed. Because the universe has existed for a finite amount of time, there are regions so distant that their light has not yet reached Earth. No telescope, regardless of size or sensitivity, can observe information that has not arrived. This creates a fundamental horizon. Beyond it, the universe may continue. In fact, most cosmologists expect that it does, but direct observation is currently impossible. This distinction is crucial. The statement, "we cannot observe beyond the cosmic horizon," is a scientific conclusion. The statement, "nothing exists beyond the horizon," is not. The second claim goes beyond available evidence. The same limitation applies to the search for a cosmic center. Within the observable universe, measurements show no evidence of a preferred location. But if the universe extends far beyond what can be observed, could unknown structures exist at unimaginable distances? Could there be regions with different properties? Could the overall geometry of the universe differ from what appears locally? Current observations cannot completely eliminate every possibility. However, they place increasingly strong constraints on such ideas. Any proposed large-scale structure beyond our horizon must remain consistent with everything we can measure within it. The second limitation concerns measurement itself. Astronomy is an observational science. Unlike laboratory physics, where researchers can control variables and repeat experiments under different conditions, astronomers must study a universe they cannot manipulate. A star cannot be moved closer for examination. A galaxy cannot be paused while its evolution is studied. The universe offers only one observable example of cosmic history. This creates unique challenges. Cosmologists often rely on statistical reasoning. They cannot measure every galaxy individually. Instead, they examine patterns across enormous populations. They ask whether the observed distribution is consistent with a model. They calculate probabilities. They compare predictions with data. This approach has produced remarkable success. Yet uncertainty remains unavoidable. Every telescope has limitations. Every measurement contains noise. Every method requires calibration. Even the most advanced instruments must interpret signals that have traveled across immense distances before reaching detectors. The third limitation is theoretical. The laws of physics that describe the universe are extraordinarily successful. General relativity explains gravity and cosmic expansion on the largest scales. Quantum mechanics explains the microscopic world with extraordinary accuracy. But these two pillars of modern physics remain incomplete together. The earliest moments of cosmic history represent the point where their limitations become unavoidable. At extremely high energies and densities, gravity should behave according to quantum principles. Yet a complete theory of quantum gravity remains undiscovered. This missing framework prevents scientists from answering some of the deepest questions about the origin of space-time itself. Was there a meaningful before cosmic expansions? Did space and time emerge from a deeper physical process? Was the earlier state truly singular? Or does another description replace the idea of a beginning? These questions remain open. Different approaches to quantum gravity, including string theory, loop quantum gravity, and other theoretical frameworks, attempt to address them. None has yet achieved experimental confirmation. The fourth limitation involves dark matter. For decades, astronomers have observed its gravitational influence. Galaxies rotate as though additional invisible mass exists. Clusters bend light more strongly than visible matter alone can explain. The growth of cosmic structures matches predictions requiring a dark component. Yet the fundamental identity of dark matter remains unknown. Thousands of experiments have searched for possible particles. Some theories have been ruled out. Others remain under investigation. The mystery is not whether something behaves like dark matter. The evidence for that behavior is strong. The mystery is what dark matter actually is. The fifth limitation concerns dark energy. The accelerating expansion of the universe is one of the most important discoveries in modern cosmology, yet the explanation behind it remains deeply uncertain. The simplest possibility is that dark energy represents Einstein's cosmological constant, a fixed property of empty space. This model fits observations remarkably well, but the value measured by astronomers is extraordinarily difficult to reconcile with theoretical predictions. The discrepancy between observation and theory is one of the greatest unsolved problems in physics. Perhaps dark energy is exactly what current models suggest. Perhaps it changes over time. Perhaps our understanding of gravity itself requires modification on the largest scales. At present, scientists continue investigating. The sixth limitation concerns the geometry of the universe. Astronomers have measured cosmic curvature with increasing precision. So far, observations suggest that space is extremely close to flat. But extremely close is not the same as perfectly known. A universe that is slightly curved on scales much larger than the observable region could still appear flat locally. Just as the Earth appears flat to someone standing in a small field, the universe might possess a global geometry too vast for current observations to reveal directly. This possibility does not mean a hidden center exists. Curvature and centrality are different concepts. A curved space does not automatically require a central location, but understanding the full geometry of the cosmos remains one of the great frontiers of science. Perhaps the most important uncertainty is not about the universe itself. It is about the questions humans choose to ask. The search for the center began with an assumption drawn from everyday experience. Large objects have centers. Expanding things have origins. Maps have middle points. But the universe repeatedly challenges those intuitions. At every stage of history, humanity discovered that familiar concepts had to be refined. The Earth was not the center of the solar system. The Sun was not the center of the galaxy. The galaxy was not the center of the universe. And perhaps the universe itself does not possess the kind of center our minds naturally imagine. This is not a failure of understanding. It is a sign that reality is more subtle than ordinary experience suggests. Science advances not only by finding answers, but by discovering which questions require deeper thought. The absence of a cosmic center has become one of those discoveries. It tells us something fundamental about space. It tells us that location may not carry the meaning we once assigned to it. It tells us that the universe does not appear organized around a single privileged point. Yet it also leaves us standing before a larger mystery. If no center exists, then what does that reveal about the nature of reality itself? Are space and time more flexible than our intuition allows? Is the universe much larger and stranger than the portion we can observe? And what future discoveries might transform even our current understanding of a centerless cosmos? To explore those questions, we must move toward the frontier where present knowledge meets possibility, the place where today's instruments end and tomorrow's discoveries begin. At the edge of scientific knowledge, progress often begins with a simple realization. The questions we ask today are shaped by the discoveries of yesterday. For centuries, humanity searched for the center of the universe because our experience taught us that everything meaningful possessed a location. Mountains had peaks, rivers had sources, planets moved around stars, stars moved around galaxies. It seemed reasonable that the entire cosmos should also have some hidden point of origin. But each advance in understanding revealed a more complex reality. The universe was not centered on Earth. It was not centered on the Sun. It was not centered on the Milky Way. And the evidence collected by modern astronomy suggests that it does not possess a center in the ordinary sense at all. Yet this conclusion is not the end of the journey. It is the beginning of a deeper investigation into what space, time, and reality itself truly are. The future of cosmology will be shaped by one central challenge. How can humanity move beyond observing the universe and begin understanding its deepest foundations? The next generation of telescopes will play a crucial role. The Vera C. Rubin Observatory will create one of the most complete time-lapse records of the night sky ever assembled. By repeatedly imaging billions of galaxies, it will allow scientists to observe changes across the cosmos on an unprecedented scale. It will refine measurements of dark energy. It will improve our understanding of galaxy formation. It will test whether the large-scale universe continues to behave according to the principles that have guided cosmology for nearly a century. Future space telescopes will push even farther. Missions designed to study dark energy and cosmic structure will measure the distribution of galaxies across enormous distances with greater precision than ever before. By comparing observations from different wavelengths and different eras of cosmic history, astronomers hope to discover whether the current model of cosmology is complete or whether subtle inconsistencies point toward new physics. The search for those inconsistencies is already underway. One of the most intriguing examples is the so-called Hubble tension. Different methods of measuring the current expansion rate of the universe have produced slightly different values. Measurements based on nearby objects, such as Cepheid variable stars and supernovae, do not perfectly agree with predictions derived from the early universe and the cosmic microwave background. The disagreement remains under active investigation. It may result from unknown systematic errors. It may indicate incomplete understanding of certain astrophysical processes, or if future evidence confirms it, it could reveal physics beyond the current cosmological model. At present, scientists do not know, but history shows that small disagreements can sometimes lead to major discoveries. The orbit of Mercury contained a tiny, unexplained difference that eventually helped confirm Einstein's theory of relativity. The motion of galaxies revealed the existence of dark matter. The brightness of distant supernovae revealed accelerating cosmic expansion. A small crack in an accepted picture can sometimes become a doorway into a larger understanding. Another frontier lies in gravitational wave astronomy. Future detectors operating in space may allow scientists to study events invisible to traditional telescopes. They could reveal mergers of enormous black holes across cosmic history. They could test gravity under extreme conditions. They might even detect signals from the earliest moments after cosmic expansion began. If such primordial gravitational waves are found, they could provide clues about processes that occurred when the universe was far younger than any electromagnetic observation can reach. They would not show us a center, but they could reveal whether our understanding of the universe's beginning is complete. Another major frontier concerns the possibility that our current theories describe only part of reality. General relativity has passed every major test so far. Quantum mechanics has passed every major test so far, yet together they remain incomplete. Some future discovery may reveal that both theories are approximations of a deeper framework. Just as Newton's laws remain useful but are contained within Einstein's more complete description of gravity, today's cosmological theories may eventually become part of a broader understanding. A future theory of quantum gravity could transform our understanding of space-time itself. It might explain how the universe began. It might reveal whether the concepts of space and time are fundamental or emerge from something deeper. It might even change the way scientists think about questions such as whether a center can exist at all. Because perhaps the deepest lesson of modern cosmology is that many familiar concepts are not as fundamental as they appear. Space is not merely an empty container. Time is not simply a universal clock ticking everywhere at the same rate. Gravity is not merely a force pulling objects together. These ideas have already been transformed by relativity. Future discoveries may transform them again. Yet even as scientists look toward revolutionary possibilities, they remain guided by a simple discipline. Evidence comes first. The universe cannot be shaped to match our expectations. Our ideas must change to match the universe. This principle is especially important when discussing possibilities beyond current knowledge. Some theories suggest the existence of multiple universes. Some propose unusual forms of cosmic geometry. Some explore the possibility that space-time itself emerges from deeper structures. These ideas can be mathematically fascinating. They can inspire important research, but they remain speculative until supported by evidence. The boundary between imagination and science is not a limitation. It is what gives science its power. A scientist is free to consider almost any possibility, but the universe decides which possibilities survive. The search for the center of the universe therefore leads to a profound realization. The greatest discoveries are not always answers. Sometimes they are transformations of the question itself. Humanity began by asking, where is the center? Modern cosmology suggests a deeper question. Why did we assume there had to be one? The assumption came naturally from our everyday world. We evolved on a planet where objects have boundaries and locations. Minds developed to navigate forests, oceans, and landscapes. They were not designed to intuitively understand expanding space-time, curved geometry, or a universe without a preferred position. Yet through mathematics and observation, we have learned to move beyond those instincts. The absence of a center is not an empty conclusion. It reveals something extraordinary. The laws governing the cosmos appear to operate everywhere. A galaxy billions of light-years away follows the same physical principles as our own. Atoms formed in the early universe obey the same rules as atoms studied in laboratories today. The same gravity that shapes galaxies also guides the motion of planets. The same ancient light that traveled across billions of years allows us to reconstruct cosmic history. The universe does not appear organized around a special location. Instead, it appears organized around universal relationships. Matter influences space-time. Gravity shapes structure. Light carries information. Time transforms the arrangement of everything that exists. The final frontier is therefore not a distant point hidden somewhere in space. It is the boundary between what the universe has revealed and what it has not. Future generations may discover new dimensions of reality. They may uncover deeper laws of nature. They may revise our understanding of cosmic origins. But whatever those discoveries reveal, they will likely continue the same pattern that has guided astronomy for centuries. Each answer opens a larger question. Each discovery expands the horizon. Each attempt to locate our place in the cosmos reveals that our true challenge is not finding a position. It is understanding the vast system in which every position exists. And perhaps that is the most remarkable outcome of the search for the center of the universe. We did not find a single point around which everything revolves. Instead, we discovered a cosmos where every observer looks outward from their own place, connected by the same expanding reality. Tonight, we began with a simple question. Where is the center of the universe? It seemed like a question that should have a location as an answer, a coordinate, a direction, a distant region waiting to be discovered. But the deeper we traveled into the cosmos, the more that assumption began to change. The universe did not reveal a hidden point where everything began its journey outward. Instead, it revealed something far more subtle, a reality where the idea of a center may not apply in the way our everyday experience suggests. For much of human history, the sky appeared to revolve around Earth. Then careful observations showed that Earth was only one world among many. The sun, once thought to be the heart of creation, became an ordinary star among hundreds of billions. The Milky Way, once imagined as the entire universe, became one galaxy among countless others. Each discovery removed another layer of cosmic privilege, yet each discovery also replaced that lost certainty with something more profound. A universe governed not by our expectations, but by principles that operate everywhere. The search for the center eventually led astronomers to the expansion of the universe itself. They discovered that distant galaxies are moving apart. They discovered that space itself can expand. They discovered that every observer, wherever they may exist, sees a similar cosmic pattern unfolding around them. This is perhaps the most beautiful paradox of modern cosmology. Every observer appears to stand at the center of their observable universe. Yet no observer occupies the center of the universe as a whole. The reason is not that everyone has a special place. It is that the universe does not appear to possess one. The center was never hidden somewhere beyond the reach of our telescopes. It was an idea based on a familiar way of thinking about objects. But the universe is not simply another object floating within something larger. It is the structure that contains everything we know. Space itself is part of the mystery. Time itself is part of the story. The cosmos is not a stage where events happen. It is the evolving framework within which events become possible. Modern astronomy has given us remarkable confidence in many aspects of this picture. We have observed the expansion of the universe. We have measured the ancient light released shortly after cosmic expansion began. We have mapped galaxies across enormous distances. We have tested predictions of general relativity. We have reconstructed the growth of cosmic structure from tiny fluctuations in the early universe. The evidence consistently points toward a cosmos without a detectable preferred location. But science also teaches humility. There are still profound mysteries. We do not yet know the true nature of dark matter. We do not yet understand the origin of dark energy. We do not know whether the universe is infinite or simply far larger than the region we can observe. We do not know the complete story of the earliest moments of cosmic history. And we do not know whether our current understanding of space and time represents the final description of reality. These unanswered questions are not weaknesses. They are the reason exploration continues. The universe has never revealed itself all at once. Each generation receives a clearer view, only to discover a larger horizon beyond it. Perhaps this is the most important lesson hidden within the search for the center. Human curiosity often begins with the desire to find our place. Ancient civilizations looked upward and asked where they stood in relation to the heavens. Modern science asked the same question with different tools. The answer was not a single location. It was a deeper understanding of connection. The atoms within our bodies were created inside ancient stars. The elements that form planets were forged through generations of stellar evolution. The light entering our telescopes has crossed unimaginable distances before reaching our eyes. Every observation of the cosmos is also a connection across time. We are not outside the universe, studying it from a distance. We are part of the same unfolding process we are trying to understand. A small planet around an ordinary star has become a place where the universe can examine itself. Through mathematics, observation, and imagination guided by evidence, human beings have reconstructed events that occurred billions of years before our existence. We have learned to read the faint traces left in ancient light. We have learned to recognize patterns across immense distances. We have learned that our intuition, while valuable in everyday life, must sometimes be transformed when confronting the scale of the cosmos. The universe does not owe us simplicity. It does not have to resemble the familiar objects surrounding us. And perhaps that is why the search for the center is so meaningful. The mystery was never only about finding a place. It was about discovering the limits of our perspective. A forest may look different depending on where one stands. A mountain range changes shape depending on the valley below. The cosmos is even more profound. Every observer sees from a particular location. Every civilization receives a different window into the universe. Yet all of those windows reveal the same underlying reality. A universe expanding, a universe evolving, a universe filled with structures shaped by the same physical laws across billions of light years. Somewhere beyond our current understanding, there may be discoveries that reshape this picture once again. Future telescopes may reveal unexpected patterns. Future theories may uncover deeper relationships between space-time and matter. Future generations may ask questions we cannot yet imagine. And perhaps they will look back on our current understanding the way we look back on earlier models of the cosmos. Not as failures, but as important steps in a continuing journey. Because every scientific answer is also an invitation. It tells us where we have arrived, and it shows us where the next horizon begins. So, after centuries of searching, we return to the original question. Where is the center of the universe? The most accurate answer we can give today is also the most surprising. As far as our observations reveal, there is no special place where everything began expanding outward. There is no hidden location waiting to be found. There is only a vast, evolving cosmos, in which every point shares the same mysterious relationship with the whole. And perhaps the final question is not where the center is. Perhaps the deeper question is this: if the universe has no center, no edge that we can reach, and no privileged place within it, what does that reveal about the true nature of reality itself?